Peter Brooks in the University of Sunshine Coast, where we run the Honey Research Lab. This particular approach has been on the bioactive components within Australian Manuka honeys. While I leave my contact details up there, I'd like to thank the CRC for supporting us for the last 3 or 4 years. Also Hive and Wellness Australia, which has supported us over about 10 years with funding and keeping our lab open. Also all the beekeepers we've had contact with over that period of time. Alright, I would love to have been there in person, but let's see how we go. We're just struggling with this technology. This project is attempted to promote Australian Manuka honeys through the analysis of their bioactive components. Those bioactives give the honey its unique properties and also its high premium price. Most people would have seen or heard of methyl-glycoxal. Methyl-glycoxal is responsible for the non-peroxide activity in these honeys. But methyl-glycoxal is not present in the Manuka nectar of the plant. Instead, there's a 3-carbon sugar called dihydroxyacetone, which converts over 1 to 2 years into the methyl-glycoxal. Apart from that, there are other bioactives which I'm going to talk about. Alright, as we go through these slides, I'd like to give recognition to the people who... Okay, these molecules that are so important for the bioactivity of the honeys do look like small sugar molecules, and very hard to separate from them by high-performance liquid chromatography. So about 10 years ago, we developed a tag that would add to the carbonyl components of these molecules and allow them to be separated from the sugars, as well as allowing them to be seen through HPLC. So the amine group reacts once with dihydroxyacetone, twice onto methyl-glycoxal, and once onto HMF. That allows us to see these molecules and separate them from the sugars present also in honeys. Alright, when breeding Manukas for improved production of these types of honeys, it is important to know how much DHA the sugar is going to produce by an individual tree, by how active that Manuka is going to be, also how much sugar is going to produce, so you have an idea how much honey is going to come from those particular plants. So, Chow Tran, one of our researchers, has been doing over 1,000 runs for collaborators, predicting how much DHA to sugar there is in a particular nectar and how much total nectar is going to be produced from that particular tree, to give you an estimate of how much honey is going to come off that. So in the selective breeding programs that we're going to let other people talk about in their presentations, most of that data has been conducted by Chow Tran in our lab. Okay, let's keep going on while I can. Alright, we also test for the honey activity as well. So using that 3-in-1 method that we developed, we analysed the dihydroxyacetone, HMF and MgO against an internal standard of anisole. This internal standard gives us a yardstick we can measure against. Okay, so DHA is going to tell you how active the honey can become after a period of time. The MgO will give its actual indicate how active that honey is now, and the HMF will tell you whether it's being cooked or as an old honey, or potentially downgraded because the HMF's gone too high. So, one of the reports that our team produces would look something like this on this next slide, where anybody who's received an analysis from us would recognise the names Chow Tran, Georgia Moore, or Linda Papaleo producing these reports. It gives you an individual result for each honey. So dihydroxyacetone, I said, came from the nectar. So young honey will have lots of DHA, but hasn't converted fully over to methyl-glycoxal yet. And the HMF tells you how old the honey is or how heat treated it is. Non-peroxide activity will tell you its antibiotic activity at the moment. So if we look at this third one across here, 2,400, that's saying it's got a lot of MgO to develop, so it'll keep that honey for longer. Whereas this honey up the top, the first honey has no DHA, no MgO, it's not a leptospermum type honey. You'd sell it on as a normal table honey. So that over our period of time has been used by beekeepers to predict how active their sites are, and we've noticed over a period of years the activity of the honeys has slowly increased because beekeepers know what to look for now. During the project, we did about 2,500 free tests for beekeepers who used the testing to determine whether the sites were actually active, producing this sort of honey, evaluating the sites, and also give them an idea how they develop over time. We've noticed over the period that we've been doing the project that the activity of the honey has been slowly increasing as the beekeepers get more of an idea what to target, when to target, and how to produce the honey. So for about 2,100 that gave us details of where the sites were, we mapped that back to the states. Most came from New South Wales or Queensland, only less than 3% from here in Western Australia. And we plotted them back to weather regions so that people weren't giving away their exact locations. That's confidential. So we see that most of them from northern New South Wales or southeast Queensland, where the most activity were coming from. During the project, we produced a what, where, and how to produce this honey instructions. So like those indications of what species are going to produce the best activity, how you tell a leptospermum from a tea tree, for example, how to mature the honey so that you get the best value out of it, how to send the honey into us if you want to test it, and how to blend the honey so that if you're trying to aim for a particular activity, you have an idea how that honey is going to mix, blend, and get you that particular activity. All these data that I'm telling you now, get my email or my phone number and send me a request if you haven't already received one of these for you. So next thing we've produced is a honey activity estimator. We get asked by a lot of beekeepers and processors, what will my honey go in 6 to 12 months? Now, when handled properly at 22 degrees, it'll mature over 18 to 24 months. On these slides, which show you sort of the printout that you would get, which you start off with, you put your active honey numbers into the start of the printout. So where you see yellow DHA 1000, MGO 200, HMF 10, that would be week 0. Then this is actually, when you put those numbers in there, it plots out a live estimation of how the honey is going to mature. So in blue on the graph on the right hand side, you see DHA dropping away slowly over 12 months, MGO in orange slowly increasing. Along with that goes the NPA value, which is in green, and grey represents the HMF. They're only changing very slowly. The next slide will show you what's happening if you heat it up a bit. So 22 degrees I would say is optimal. 37 degrees on the left hand side of the graph tells you what's going to happen if, for example, you leave your honey out in the sun. And this one goes over 6 months because things start changing faster. You see that the blue DHA drops away very quickly, but the MGO is not increasing the same rate as you might expect. Instead, it's being destroyed by the heat also. And you'll see that after a slight rise, it starts dipping down again, along with the NPA value. Whereas the HMF, which is in grey, starts going up within 6 months at 37 degrees. That's about 400 ppm, way above the limits. At 65 degrees, if you put your honey, for example, in a warm room to try to speed up the process, you see that the MGO in orange never increases, it actually starts dropping away, destroying it. It's thermally unstable, along with the DHA. And also the NPA is dropping away. You'll notice also this one's in days. So within 1 week, you've converted your honey over to Vegemite. So the take-home message is do not heat your honey. Otherwise, you turn it into Vegemite. It's active. You also get requested quite often from beekeepers and processors how to make a honey to a certain activity that they need to fill a market. So look at example number 5 there, for example. Somebody wants to make a honey that's 120 MGO. We always say aim 10% above that, just in case you undershoot and you have to re-label all your honey again. So let's say they want 120 ppm, aim for 132. And how many kilos do they want? They want 200 kilos of that particular honey. You're going to start off honey A that has 400 ppm in a highly active honey, and 80 ppm in a less active honey. You're going to blend those two to make it 132. Then the honey A calculation tells you need 32.5 kilos of that honey A, the more active one, and about 167 kilos of honey B, the less active. Tell you how to blend those honeys in what proportions to make those sort of calculations out. Right, these last couple of slides are on the other bioactives you might find in honey, which is the phenolics. If you're taking Manuka honey on toast, you're not eating it for the antibacterial activity, you might be taking it for the antioxidant activity. If you're putting on the wound's got to heal. You're not just looking at killing the bug, but also healing the wound. The phenolics in Manukas have been linked back to the antioxidant and also the anti-inflammatory activity of those. So we're developing at the moment, which is going to be a talk on Thursday morning, about analysis of these sort of actives in honey, the phenolics and the flavonoids. Right, just quickly looking at 3 different species of leptospermum, polygale, whitey-eye, levacidea, and scroparium, using our published method for DHA-MgO. We can get these values off there. And then just looking at all those phenolics in that last trace, we start getting out numbers of ppm values for the other components. Leptospermum is another one that's very well known in these particular molecules. I'm just a little bit conscious of time right now, so I better hop on to our final slide, which is our crew. Georgia Moore and Linda do most of those honey analyses. Georgia has also done most of the phenolic analysis. I've been driving her insane lately trying to get those done. On to the right-hand side of me is Dr. Man Norton, the man that developed that nectar analysis. And she also moved down to Madeline Beekman's lab and did deformed wing virus research before coming back up here. Chow Tran, who does a lot of the honey analysis for us, also did that 1,000 plus nectar analyses for CRC collaborators. All right, let's see, I'm at 13 minutes now, so I better stop. My contacts are up here. I'd like anybody who'd like to talk to us about honey analysis, give us a ring or an email, contact us please. All right, goodbye. I'll stop now and open up for questions.